Never be afraid. There's nothing which is known which can't be understood. And there's nothing which is understood which can't be explained. For over 50 episodes now, my team and I have brought you to the very frontier of knowledge in physics and astronomy. And still, our mission goes on. To present you with your birthright, an understanding of the universe. I've traveled the world seeking out a certain type of genius. Masters of not only their academic disciplines, but also at explaining their research in understandable ways. And I've bestowed upon these women and men the title of Titanium Physicist. You're listening to the Titanium Physicist podcast, and I'm Ben Tippett. And now, allez, physique! It is important that you understand that nothing in this universe is insignificant. There's no breed of object or thing which does not have the capacity to accomplish amazing feats. What's that? Did I hear you mention the humble photon? Did I just hear you tell me that photons have no weight and carry very little energy, and that the most they can do is shove an atom around but never shatter it? That they can move electrons around but they never lay a finger on the meat of the atom, its dense, impenetrable nucleus? Did I hear you mumble then about the pitiful neutrino, the byproduct of nuclear reactions, but of almost no weight or significance, destined to pass through the Earth like a ghost and wander the universe with almost no hope of even twisting the path of an electron or atom? Well, let me tell you about how the largest stars in the universe die. A star is a story which gravity tells matter. It's a story of thermodynamics. It's a story of progress. A cloud of gas up in space collapses on itself from the effects of its own gravity pulling itself in, and as it does so, it heats up. And as it heats up, it glows, and as it glows, it loses energy to the outer space. There's never a moment of its life when it has more energy than it did before it collapsed. The ratchet of thermodynamics means that it's always destined to collapse and never expand because it's always losing energy out into space. Now, the denser it gets, the hotter it gets, and atoms start to squish together. Hydrogen atoms become helium, helium becomes carbon, carbon becomes oxygen, and oxygen becomes silicon, and silicon becomes iron, and each step gives you a heavier element. Each step releases more energy, which is also destined to radiate out into space. The bigger the star is, the faster it all happens. Stars are stories that gravity tells matter. The story says that lighter elements become heavier elements. The story says that everything's going to end up in the middle, clumped together. The story says that it's all inevitable, that everything's going to join the middle and turn to iron and cool down. But if things get hot enough, this story always fails to unfold in this way. The outer part of the story will explode outward, emitting light and launching an envelope of gas into interstellar space. It's a famous event. You've heard of it. It's called a Type II supernova. So who is responsible for this? Which character, which particle is responsible for overturning the inevitable crush? It's the humble photons and the pitiful neutrinos. At the core of the star, the photons become so energetic that they shatter the nuclei in the iron core and dramatically change the politics of pressure and gases which dictated everything up to that point. And the neutrinos are made in such flooding abundance that they push their way out, driving the explosion. So sure, we might think on our provincial planet, around our provincial star, that neutrinos and photons are inconsequential. But remember that they're the key players in the most dramatic events in the universe. It's important that you understand that nothing in this universe is insignificant. Today on the Titanium Physicist podcast, our topic is Type 2 supernova. So speaking of the inevitability of exciting events, there's a book coming out soonish about technologies which are going to rock our world in the near future. The book was written by two friends and past guests of the show, and I'm super excited to have one half of them back. Today's guest is the co-author of the book called Soonish, as well as the author and artist of the Saturday morning breakfast cereal webcomic. Welcome back to the show, Zach Weinersmith.
Thank you.
So Zach, today I've assembled two favorite titanium physicists in a new and interesting combination. Arise, Dr. James Sylvester. Dr. James got his PhD from Queen's University in Kingston, Canada, and he's currently a researcher in stellar astrophysics at Uppsala University in Sweden. And arise, Hanalore Gurling-Dunsmore.
Wow.
Hanalore got her master's degree from Caltech, and she's currently a researcher at NASA's Jet Propulsion Laboratory. She's an expert in structure formation in space. All right, everybody, let's talk about big booms in the dark. So, why don't we talk about these supernova things? Zach, do you know what a supernova is?
Yes, but not substantially beyond what you said in your introduction, so I'm excited to learn more.
So supernova are really, really, really bright things that happen in the night sky. And the interesting bit here is that they were cataloged before we had any idea of what they were. Essentially, so the famous jerk astrophysicist Fritz Zwicky and his collaborators, they were cataloging all these different really, really bright temporary explosions. Nova means new, and so it's a new bright thing that wasn't before. They're essentially big explosions in space that don't last all that long, but they're as bright as a galaxy. So even if one happens in a far, far off galaxy, we'll still be able to see them. And so they were cataloged before we had any idea of what they were. So mostly when people talk about supernova, they're talking about the thing we were talking about in the introduction, a star blowing up, right? But that's called a Type 2 supernova. And the reason is, essentially, when they were cataloging the phenomena, they weren't listing them in any particular order. So a Type 1 supernova is when there's a star and it has a companion star. And if that companion star is a type called a white dwarf, it won't be heavy or big enough to kind of explode. But if it has a companion star, sometimes the companion star kind of shoots gas and dust onto it, and then as that white dwarf gets heavier and heavier and heavier, sometimes it can go critical and blow up. So that's a Type 1 supernova. The type we're talking about today, Type 2, comes about when you have a star and it's really, really big, and it reaches the end of its life, and it explodes, okay?
You also can get that with Type 1b and Type 1c. The B and C indicate commonalities in spectral behavior, just for people's personal edification, I guess.
Long story short, the supernovas that we're used to talking about, somebody will be on Star Trek and they'll be like, there's a supernova happening nearby. That's usually Type 2.
Yeah, so if I were in Star Trek, Type 2 and Type 1 would both be super predictable, you would be able to time them, just by looking at spectral analysis or something like that?
So there's something called a light curve, which is basically just a plot of luminosity coming from the star over a period of time. And Type 1As pretty much have identical light curves. And so they all behave very, very, very similarly. So the difference between Type 1A and Type 1B and Type 1C is when you look at the spectrum, not just the luminosity, but of the frequency, which can tell you what's getting absorbed and what's not. And that can thus tell you what the composition of the star is. What we have is, in a Type 1A, there's no hydrogen in the spectrum, which tells us that the hydrogen envelope is gone, which is why we think that they happen in binaries, because in order to strip the hydrogen envelope rapidly enough to see them as often as we do, basically that needs to be getting stripped by a companion star rather than it just getting exhausted. Whereas a Type 2 has hydrogen in the spectrum. And then within Type 1B has no Balmer hydrogen lines, and it also has pretty much no silicon lines, but it does have strong helium lines. And then Type 1C don't have hydrogen, helium, or silicon.
So what causes the second star in the system to strip particular elements?
Gravity. It's accretion.
Yeah, but I mean, like, how does it know to pick hydrogen and silicon, say, instead of,
Of course. This is because hydrogen is the outermost shell of the star.
Just because it's so light?
Yeah, and that's also what a star starts off as. So let's go a little bit further back. So there are gas giants and there are stars, and they both are gravitationally bound balls of gas in the night sky. The difference is that stars undergo fusion. And they start off as just hydrogen, maybe with a little bit of helium, but they basically just start off as hydrogen. And that hydrogen undergoes fusion. As it's undergoing fusion, eventually, so just as burning a log will deposit ash, the hydrogen fusing will deposit a quote-unquote ash of helium, and that creates this next shell within the star, which is, closer in, because it needs to be in a region with more energy and therefore it's hotter in order to get that fusion. And so that's why, is because the hydrogen is the outer shell, both because it's the lightest and also because it was there first, and everything else, in order to exist, has to be further in where it's hotter and more energetic.
So you said in type 1C you wouldn't see silicon in the spectrum, is that right? So how would it get something heavy like silicon out?
The thing that's a little bit tough about 1Bs and 1Cs is that they're a little bit harder to see. Like for type 1B and type 1C, because those are less massive stars, so it just might never get hot enough to fuse down to silicon.
Oh, I see. So it never made the silicon in the first place. It's not that it got stripped.
Right.
So like with both type 1 and type 2, is it like you couldn't tell what was going on from a snapshot of the spectrum, but if you had like, a continuous sequence over some amount of time, you could tell what it was pretty readily?
If you got a snapshot of the spectrum and you knew at what temporal region in the light curve that snapshot was from, yes, you could tell if it was type 1A, type 1B, type 1C. But if someone just handed you a spectrum and said this came from a star at some point in its life cycle, it would depend on how pronounced the features are. Something that's kind of neat, just going back to what Ben was saying, is, we've seen type 2 supernova throughout antiquity. They're actually recorded. And so it would have looked basically like a new star appearing in the sky. Of course, at that time, people took that sort of thing to be an omen. Now we take it to be, the death throes of a star.
So if you were there, like, how long would the new star persist in the sky?
So the light curves from a supernova really only last about a year. The peak of that lasts for about 2 months. And then from there, it drops pretty precipitously.
It's more than linear. There's like a spike for 2 months, and then it just slowly, it fades away quickly. I feel like that'd be really freaky if you didn't know what it was.
Oh, yeah. I mean, so many things in the sky were terrifying, I'm sure, at the time. And I think that's probably why they looked at them to be omens. I mean, think about the eclipse. That would be horrifying. Just for a few minutes, every, generation or so, the sun goes away.
Even today, it's like hard to predict a supernova, type 2?
Yeah, so it depends on how detailed of a prediction you're making. For example, we're able to look at the spectrum of the star Betelgeuse in the Orion constellation and say, that one should be going supernova pretty soon. And we actually expect to see that happen within the next 5 to 10 decades. So within the next 50 to 100 years, we expect to see Betelgeuse go supernova.
Really?
We can't. Mm-hmm.
And it'll just be gone.
Well, it won't be gone quite yet. We'll get a little bit. So we can look at a spectrum and say, yep, this star is going to go supernova sometime pretty soon. We can kind of give you an idea of, is this star young? Is this star middle-aged? Is this star old? But we can't time it. We can't say, and on this exact day at this time, the flare should happen. So I guess it depends on how precisely you mean predict.
I mean, within the life of a star, getting it within a few decades is pretty tight, it seems to me.
Well, I mean, so the reason why you can do that is because actually the time frame of the end of the life of a star is actually super, super quick. So,
okay. Hydrogen burning lasts tens of millions of years. Helium burning lasts millions of years.
Carbon lasts about 1,000 to 10,000 years. Neon lasts about 100 to 1,000 years. Oxygen is less than a year, and silicon is days. That's it.
At this point in the game, I think maybe we should back the Truff Cup and set it properly on the tracks of exactly how the inside of a star works.
So, as Ben already mentioned in his introduction, stars have very varying lives, very different lives. You have very small stars, very large stars. And typically I like to think of stars, they're sort of analogous to musicians. So you can have a very quiet, precise classical music musician who will have a very calm life and will probably live for quite a long time. But then you have these rock and roll stars that have very fast lives and they tend to die younger. And this is kind of what happens with stars. So you start off with the very small, cooler in temperature stars, and these are the stars that have very long, stable lifetimes. And then if you look at the more massive stars, these are higher also in temperature, these have very short lives, and also they tend to end more violently. So this is where the sort of analogy of musicians can come into play. So if you look at the stars in reference to, for example, temperature and colour, they all follow certain trends. So if we talk about the more massive stars, these are the stars that have higher temperatures, and also these are the stars that generally, when you look at them visually, they look bluer. So this is the very blue stars. And then we have middling stars. So these are stars that have temperatures ranging, just to give an example, of about 10,000 to 5,000 Kelvin. It's quite a long range there, but it gives you an idea. And our star, the sun, is sort of in the bottom of that range I mentioned. And this is quite a very small star, not particularly massive, but for us it's very lucky because it has a very long lifetime. It lasts for 10 billion years. Well, that's the average lifetime. And so this is great for life because if it was one of these rock stars, as I coined them, we probably wouldn't be here already because the star would have already blown up and done something quite nasty. And then when you get down to the cooler stars, and these are the redder stars, have temperatures around 3,000 Kelvin. So these are stars that actually last for quite a long time and have very stable lives that end not particularly in an exciting way. One thing I like to draw people's attention to, particularly when we look at the stars, is that I talk about the colour, and now people instinctively think, well, why are the hotter stars blue? Because, people maybe think, oh, blue's a cooler temperature. And I usually get people to think about if they did experiments at high school with a Bunsen burner. I certainly remember my teacher telling me that the yellow flickering flame was the safer flame, and the flame that was blue and violent was the hotter flame you had to avoid. So that's always a way of linking in the temperatures and the colours. So the blue stars are really hot. Sort of yellowy stars are in sort of middle range, and then we have some sort of redder in colour stars, which are the cooler, less massive stars. So that's kind of how the stars are kind of thought about in a population sense. And then the evolution of such stars can be quite distinctive. So the very small stars, nothing really violent happens. They end up in a state which we call a brown dwarf. Slightly larger stars can become red dwarfs, and in certain situations they can evolve into white dwarfs. And then we have medium-sized stars, and these evolve from yellow dwarfs into red giants, and they can become planetary nebula in certain situations where you see these very interesting structures in space as the gas is blown out from the star, and they can end up in a white dwarf. And then when we get to the big stars, the rock and roll heroes that we're speaking about, then we start with these blue giant, and as it evolves it can go to a red supergiant, and this can end up in a supernova, as we're going to discuss in detail. And then as they evolve further, we can either get neutron stars or a black hole depending on the mass of the star in question. So that's kind of how, very simplistically, how the stars differ in the sky. So they're all different and they all lead different lives.
One of my favorite science facts is the reason why plants on Earth are green is our sun actually emits most strongly in green light. And the thing is you might think, oh, hey, shouldn't plants be wanting to absorb that green light rather than reflect it to harness that energy for photosynthesis? But what it turns out is that the energy flux is so high that it would damage the cellular structures of plants. And so reflecting the green light is actually a way that plants protect themselves from the damage from that radiation, because it's just got so much energy. And so the absorption spectrum of chlorophyll has a strong peak in the blue light, which that light is utilized for photosynthesis. And then the red light actually also has a small peak, and that's used for orientation of leaves. So
that's awesome. I didn't know that.
Yeah, science is cool.
So, this is totally not on topic, but can you make like a super plant that can withstand all the energy and take all of it?
I mean, I'm sure that you could. I don't know how you would do that.
like mutant chlorophyll.
As a result, we can expect that plants on other planets would be different colors, depending on what their stars emit most strongly.
Just whenever people talk about colors of stars, I always like that, because now whenever I walk around and I see green plants, which is not as common as you would think because I live in Southern California, but, then you think about it and it's kind of a cool thing.
So there was who was it Lord Kelvin who tried to calculate the age of the sun? There was a mystery about the age of the universe and the sun. The presumption was that the reason the sun was hot, it was clearly not burning, wood. The sun is clearly not made of fire, but it's really hot. And so the question was, why is the sun so hot? And one idea was that the sun was just hot because of thermal interactions. So it started out as a big cloud of gas. It collapsed down, but as things collapse down, essentially everything's falling towards the middle. Gas particles bump against each other. That turns into thermal vibrations. That turns into temperature, right? So this definitely would cause our collapsing ball of gas to get really hot. And then if it was hot, it would radiate energy out into space. And so the question was, how old is the sun if this is the process that's causing it to be hot? And the answer was that the age of the sun was way, way, way too small. But isotopes on the Earth suggest that the
It's Kelvin-Helmholtz. It's the Kelvin-Helmholtz timescale, and it's just basically the gravitational potential energy over the luminosity, and it should be about 3 times 10 to the 7 years.
Right, so 10 million years, right? And that's no time at all, cosmically. So we knew that this couldn't be right, because if this was the reason the sun was puffy and bright, that the sun would have exerted all this energy and would have collapsed smaller and been cooler and dimmer as a result. And so the question was, what's causing the sun to be bright? What's causing stars to puff up the way they do? And the answer is, in the end, it had to be nuclear fusion. So particles inside the sun colliding, like 2 hydrogen atoms has a higher mass than 1 helium atom. But you need 2 protons together to make a helium atom. And so E is equal to mc squared. The difference in their masses as our 2 hydrogen atoms become a helium atom gets turned into energy, thermal energy, photons. And so release of energy from nuclear fusion is the reason our sun hasn't run out of heat.
Yeah, and that's our nuclear timescale, which is this energy released through fusion over luminosity. And that actually gets you to the right order of magnitude. Like that simple of a calculation gets you to the right order of magnitude for the age, like how long our sun will live.
So the interesting beast here is this, what's causing this nuclear fusion? Nuclear fusion isn't something we can achieve in a controlled way in any type of efficient way on Earth, because it just requires immense temperatures, immense energies, immense pressures to overcome the electrostatic force and get 2 protons close enough together that they'll stick together using the strong force, gas.
The big reason why we're struggling so much with getting fusion to work on Earth actually is that we can't confine the plasmas well enough. So the hottest plasmas that we make are made in something called a tokamak. All you need to know about tokamak is it's a certain geometry of this reactor. And the problem is that we can't get the magnetic field strong enough and fine-tuned enough to keep the plasmas from running into the sides of the tokamak and cooling off. We can get the plasmas to a high enough energy momentarily. It's just that then they cool. So this is actually one reason why room temperature and what we call high temperature superconductors are super exciting, is because that could potentially help us with getting fusion, which if we get fusion, ta-da, our energy problems are solved. Especially because fusion reactions actually don't produce the same kind of harmful byproducts as fission reactors. And actually what's really cool is that you could line the walls of a functioning tokamak or a functioning fusion reactor with the byproducts of fission, and it would actually make the fission byproducts essentially harmless.
We actually for the book we wrote, we actually did a fusion section, so I'm more or less up on the depressing state of fusion research. It was the one section we had, because we're mostly doing like emerging future stuff, and so usually the people in these fields are kind of upbeat and or crazy. Whereas in fusion they're a little more staid and like pessimistic. Which is not surprising, given that, like, ITER is going to take whatever it is, 20, 30 years to build and, like, maybe work.
Basically, the problem with ITER is that the simulations that we did for designing it are way, way too old. And as we have improved our simulations, all of them are basically showing that ITER is not going to work a long time. So ITER is going to be online pretty soon, actually. I think within a decade or so. But the thing is that ITER has cost so much money that when it fails, it's going to be really, really hard to get funding for an improved version. And this is why I got out of fusion, was like sitting at Oxford one summer and just listening to all of these people talk about all the way ITER isn't going to work. And I just was like, this is not a good career move, I feel like.
I kind of feel like researching soured me a little on just the general idea of international consortia for mega projects. Like, NIF got built much more quickly. I mean, it was NIF, so, like, whatever, but it got built quickly and way cheaper. It failed faster. And it seems like ITER's been just a mess keeping funding together between however many nations it is.
So I've got a question. Can they do that thing that LIGO did? They knew LIGO wasn't going to work for the first 10 years of its operation, right?
The difference is that LIGO was always meant to be exploratory, like knowledge for knowledge's sake, and ITER is essentially supposed to be an engineering project. The funding for ITER was given because we were supposed to be getting like a sustainable and eventually cheap energy source.
But they can't just go, well, now advanced ITER is coming online and we fixed the things that won't work, and in 5 years we're going to have it.
I mean, we can try. It's just a question of if we can convince the politicians, because the problem is we've been saying that we're 5, 10, 15 years away from fusion for a few decades now.
Yeah. The really depressing part to me was, like, even if ITER works great, what that means for the world is there's a $30 billion type of reactor you can build, and $30 billion, for reference, is the cost of, 15 conventional nuclear fission reactors. Like, even if it works, the capital expenditure math doesn't add up unless someone really fixed the cost problems.
I mean, part of this also is the fact that fission reactors are actually pretty safe if you let scientists design them. The problem with Fukushima was that they let business people make decisions on what the storm wall was going to be, rather than listen to the scientist recommendation. But
totally agree, yeah. And can I say, for reference, like, the upper limit case is that 1,500 people will experience premature death as a result of Fukushima, which is
But the word nuclear is scary. Nuclear is a scary word.
This suddenly became like a political episode. I assume this is all getting cut, right?
Every episode is a political episode. Science, unfortunately, is politicized.
The moral of the story is nuclear fusion is something that requires immense pressures, immense temperatures. It's really hard to do and confine. But on the inside of a star, in the middle of the star, where the pressure is really high and where it's really, really hot, nuclear fusion can happen. And so the story of the stars that James was telling you, where a star will puff up, turn into a red giant, or a star will puff up really big and turn into a red supergiant and explode. What happens to a star essentially is dictated by what kind of fusion is happening in the core. Long story short, if your star isn't heavy enough, you can't get any fusion in the core. In fact, our star is barely heavy enough to get fusion inside of its core. Fusion happens in the core of our sun only by virtue of quantum tunneling.
So, basically, we were talking about giant stars, right? So, for example, red giants. You start with a red giant that has enough heat to fuse helium into carbon. So you get these two fusion processes occur in the core. And then basically what happens is, at some point, the star runs out of helium. So then it goes into a more complex situation. So it starts to collapse and heat up, and this causes the outer layers of the star to expand and cool, and you end up with basically these onion shells that we were talking about earlier. And so in these shells, you have, in what we now call a massive red supergiant, you have a hydrogen-burning shell, a helium-burning shell, a carbon-burning shell, an oxygen-burning shell, a neon-burning shell, silicon-burning shell, and then an iron core. These supergiants have high enough pressure and temperatures that they can fuse these elements heavier than, for example, carbon and oxygen. And this is where you have this sort of onion layer sort of structure going on. And this is the stars that will eventually end up in the supernovas, which we're discussing today. Yeah.
Long story short, you end up with a temperature and pressure gradient inside these heavy stars. And depending on what phase of its life it's in, you're going to get nuclear fusion happening at different locations. So at the very start, everything burns hydrogen in the middle. And that energy is what holds the ball of gas aloft. If it starts to run out of hydrogen, the pressure and temperature of the gas in the middle can no longer hold the weight of the star above it, and so it starts to collapse down. And if it's heavy enough, if the star is big enough, the temperature and pressure in the middle can exceed the point where it can start burning helium. And this procedure happens over and over depending on how massive the star is. So it's possible for a heavier star to, burn out all of the helium in its core, because it's going to run out of helium in its core first, because its core is where the temperature and density are the highest. So when it runs out of helium to burn in the middle of it, it's going to start collapsing down again. The pressure and density in the middle is going to increase. It's going to start burning. It'll start combining carbon atoms, nitrogen atoms, oxygen atoms. And the idea here is that it's going to run out of fuel for this fusion in the middle parts first. And so what you happen is essentially one of these really, really big stars, you'll end up with two concentric shells. Outside a certain radius, it'll still be hydrogen burning, but inside a certain radius, it'll be helium burning. And then when inside that radius in the inner core, it runs out of helium to burn, it'll start burning heavier and heavier elements. Each stage of this procedure can only happen if the star is heavy enough for the pressure in the middle to exceed a temperature and density. If the star isn't heavy enough, it just won't burn those heavier elements, and it will just kind of settle down and keep on collapsing. And so these bigger stars concentric down into the middle where it reaches iron. That thing I said before where if you combine two atoms of hydrogen, you end up with an atom of helium, and the atom of helium has a lower mass than the hydrogen, and so that difference in mass turns into energy. Once you reach iron, that's no longer true. You can combine two iron atoms. So the resulting atom that you get from that will be heavier to atoms that made it up. And so it's no longer energetically favorable. It no longer releases energy, this fusion procedure. And so these giant cores of stars stop burning once they reach iron. And so you end up with a big ball of iron in the center of the star, and then nuclear fusion in concentric circles as we get out to farther radius. So let's talk about how that goes wrong.
So the first thing that I want to say is it might not be entirely obvious why we keep using a massive star as synonymous with a hot star. In order to think about that, let's step back to something that I think a lot of people are familiar with, is the ideal gas law. And the ideal gas law is pressure times your volume equals some multiplicative constant times the number density times the temperature. And so in a massive star, the pressure is higher because there's more mass. This is just the pressure from the gravitational force of the star on itself, which is holding the star together. And as a result, as that pressure increases, so is the temperature going to increase. What temperature really is the kinetic energy of the particles of matter. So your electrons are bouncing around faster and faster. Things are able to fuse. So this is why the mass of the star ends up translating to temperature. So along similar lines, your iron core of a massive star, the reason why it doesn't contract immediately is because it's supported by what's called electron degeneracy pressure, which comes from the Pauli exclusion principle, which states that fermions, that is to say particles with half-integer spin, cannot occupy the same region of space with the same energy level at the same time. All right, that's pretty intuitive. I don't think anyone here is occupying the same exact region of space at a given point of time as anything else. But this is not some law that can't be broken. It's just something that in most regimes, it's stronger than any force that's pushing things together. But stars are really massive.
The way to think about this is there's essentially a limit on how many electrons you can put in a box. Essentially on the inside of a star, it's electrically neutral, but it's a plasma. There's lots and lots of electrons and they're running everywhere, but there's the same number of kind of positive charges from protons. So you're familiar with the Pauli exclusion principle? you learn it in high school when you're talking about like putting electrons on like atom diagrams, right? So you draw all the shells and you're like, every shell of this atom gets 2 electrons, and you can't put any more than 2 electrons on a particular shell because it violates this principle. So essentially, there's a limit on how many electrons we can stuff into this box at a certain pressure. The deal is that inside your stellar core, only 1 electron can have each kind of defining, well, quantum number, defining its energy, right? Each additional electron you shove into there has to have a higher energy than the previous ones, and you end up with an overall kind of a pressure because you can't have any more low temperature electrons. All of the low temperature electrons are already in there, so the more electrons you stuff in, the denser it gets. These electrons are going to have really high energy because all of the lower identities are taken, and so they're going to kind of push back. And so you get a tremendous amount of pressure. And now it's the photon things. The idea here is that photons, particles of light, they don't usually, say, shatter nuclei. Like, you've never heard of like a light where you shine light on a helium particle and it splits it into 2 hydrogen particles? But it gets so hot that you get really, really high energy photons if the temperature reaches a certain point. And these photons are capable of smashing iron nuclei into pieces. And so when they do that, you end up with a bunch of protons flying around. They're not iron anymore, they're just random protons. And in those high pressure situations, those protons can get squished together with some of the free electrons to make neutrons, which are, well, electrically neutral. But the important thing is these neutrons, they pull electrons out of circulation. And the problem was that these electrons were degenerate, it's called. Them as a community were what's holding up the center of the core. So as soon as you reach that limit, suddenly the core loses a ton of its electrons, and in doing so, its pressure drops, and the core can't hold itself up anymore, and so it collapses.
And so this is the beginning of the intuitively titled core collapse process. So we lose this electron degeneracy pressure, and as a result, we have nothing really pushing back against that gravitational force of the core. And so it starts to contract, and it keeps on contracting. And the thing is if the inward pressure is so great that it overcomes the outward pressure of electron degeneracy, there's not much that's going to stop it until you get to length scales of the nuclear force. So all this matter is falling in, and this happens over the course of a few milliseconds. And then we get to the regime where the nuclear force, which is usually attractive and it holds nuclei together, becomes repulsive. Now, what's really, really cool about this is that we actually don't know a lot about the nuclear force in this regime. And part of the reason is that the only place this really happens that we know of is during core collapse. We can't replicate these conditions in a lab, at least certainly not at this point. And so we don't know much besides the fact that the nuclear force becomes repulsive. And this is one of the reasons why core collapse supernova are one of the most interesting laboratories in the universe, is because it's this completely wild phenomena that's happening. So the nuclear force actually starts to push back. You can think of it as essentially the neutrons pushing against each other, the same way that the electron degeneracy pressure is the electrons pushing against each other. Again, I just want to really drive home, this is a lot of mass. I mean, that's how we're able to overcome that electron degeneracy pressure. And yet the nuclear force pushes so hard against further compression that it actually is able to send the mass of the core back out with a ton of kinetic energy. And this is what we're going to start calling the shock. So, you with me?
Me? Yeah.
Yeah, cool, awesome. Okay, so the shock is now moving outwards. But the thing is that stars are really big. And the thing that was really collapsing was this iron core. And so the outer shells take a minute to realize, oh, hey, wait, we can start moving inwards because we don't have that pressure pushing out against us. And, part of that is because information can only travel any faster than the speed of sound in the plasma. So the information that the outer boundary of the core has moved inwards, that's not going to propagate to the outer shells of the star any faster than the speed of sound in the plasma. And the reason why it's the speed of sound is because these are pressure waves, and speed of sound is how fast a pressure wave can move through a medium. So what we have are the outer layers still falling in, and the now bounced core giving a shock that's moving out, right? at some point these are going to meet. And because there's a lot of mass falling in, that's going to have a lot of what we call ram pressure. And that ram pressure is enough to actually stall that shock, which again, let's really think about this. The shock has so much kinetic energy that it was able to overcome the electron degeneracy pressure to move out. But that's how much pressure is coming in from the infalling matter, is that it's able to stall that, which is kind of wild, I think. So now we get this battle of the wills, right? And this is where things take one of two paths. One is that the infalling matter has so much ram pressure that it overcomes that shock and it just piles on and it propagates all the way down to the core and eventually, and by eventually I mean within a few milliseconds, overcomes the Chandra-Shekhar limit. And so those give you a black hole without an explosion. And those are called failed core collapse supernovae. So that's what happens when the shock fails to revive and fails to keep moving outwards. Sometimes, though, the shock does revive. Now, how does this happen? Again, remember, we have a ton of kinetic energy coming with the shock from the bounced core, right? In order to stall that, you need a lot of pressure from the infalling matter. What's giving you all that pressure is super high density of matter. And because of that high density, where the shock is stalled actually becomes opaque to neutrinos. That is to say, neutrinos, which essentially have zero mass, they can't find their way through. They can't wiggle through little gaps in the matter. And so now how I kind of visualize this is a little bit like putting a lid on a pot of boiling water. At first, it's just, you're not going to hear anything. You're not going to see anything. It's just the lid's going to get a little steamy. But if you leave it on there and you keep that water boiling, that lid's going to start rattling, right? Because there's enough energy from that steam that's pressing up on that lid and it starts moving the lid around. So this is what's happening this is called the gain region. This is where the neutrinos are essentially boiling, basically ramming against the shock front, then going back, and they're getting more and more and more energy. And eventually, if the ram pressure doesn't overcome shock, the neutrinos are what revive the shock. So as the neutrinos gain more and more energy, just like the steam gains more energy as you leave the lid on the pot of boiling water, eventually these neutrinos have enough energy that they're able to push back that shock, push that outwards. And that's said to be the revival of the shock. And depending on how much energy those neutrinos have, you're going to get different observable phenomena. But that's how you get a successful type 2 supernova. And you're going to end up being left with a neutron star. That's what's going to happen to the core that didn't, explode out.
Let's review what's going on. Essentially, we start out with a normal star. It's in equilibrium. Essentially, all the pressure at each point inside the star is supporting the weight of everything above it. Suddenly, the core collapses. You get all these electrons being absorbed by all these protons that were knocked free by the really hot photons. The iron core collapses down. It loses electron degeneracy pressure, but there's another type of pressure that can sustain it at a much smaller density, so the core collapses down, becomes a really hard ball. The matter above it starts to flow inwards, so it's gaining momentum as it falls inwards, and then it hits the solidified core and it bounces outwards. And this produces a shock wave that moves outwards. The shock wave can't just move outwards and blow the shell off the star because matter's still falling in. I want you to imagine it's Black Friday slowly coming up, right? So imagine we're at one of those big Black Friday sales. Imagine we're in a cold place like Ontario or Michigan where all the malls have two sets of doors, like an airlock, an outer door and an inner door into the store. So everybody's in the parking lot. There's a big crowd of people wanting to get into the store. The people closer to the door are more closely packed because they're all excited to get in. Farther out, it's less closely packed. And then they open the outer doors and the people start to flow in. They're like, yay, the store's open. But the employees haven't unlocked the inner doors. So the people flow into the airlock and hit the inner doors. They bounce off the doors, but there's still a crush of people who've heard that the store is open and have started filing in. So the people telling the people behind them, the word of mouth news that the store isn't open, traveling outward, that's the shock wave. And so you end up with a shock wave moving out, but it has to pass through this group of people that are moving inwards. There's an issue here where sometimes the shock wave can't travel out fast enough because the matter flowing inward is moving too quickly. There's a couple issues here, like how the speed of a wave depends on the density. The more dense it is, the slower the sound wave travels. So what happens is essentially we end up with a shock wave front. All of the energy is building up in this one location where it's trying to move outwards, but it can't because of the crush of matter moving inwards. Sometimes this crush of matter falling in wins, and it drags the shock wave down into the middle. That's called the failed core collapse supernova. But the really exciting, the really bright ones are when the shock wins. But what could cause the shock to move outwards fast enough with all this matter falling in, trying to pass through it? And the answer is, it starts to cook. You know, a shock wave, it's a pressure wave. And so the matter at the location of the shock wave is really, really, really dense. And the density of matter is so high that neutrinos can't pass through. But inside that radius, the density and the pressure and the temperature are so high that they're making neutrinos like gangbusters. They're making lots and lots and lots and lots and lots of neutrinos. And these neutrinos just keep building up and building up and building up. And if they build up strong enough, they can propel the shock wave out farther, faster, extra hard. It's possible for a star to lose up to 10% of its core rest mass in neutrinos in that procedure. So we think that supernovae are really bright in terms of luminosity, but that's nothing to compare to like the crazy neutrino flux that's required to blow the lid off the pot, in Hanalore's expression. So we have actually detected neutrinos at the same time as we've detected supernovas. In the 1987 supernova, we had some neutrino detectors there.
I think it had to have been Kamiokande.
Yeah. We've detected neutrinos that were produced in this process, and it's totally bonkers.
Something that's equally important that supernova do, and I would say more exciting, is that as we were talking earlier, we make all these heavy elements in the process of the star burning. And those elements still exist as the star collapses and then explodes. And that's actually where we get the heavy elements that make up our bodies, like the calcium in our bones and the iron in our blood. It's like we are literally made out of these elements that were produced in the process of getting to a supernova.
Stellar fusion can only account for material up to iron, right?
Yep.
And the fact that we have elements on the Earth that are heavier than iron is because it was all formed in the shockwave of a supernova.
Yes. Or everything that we get that's much heavier beyond neon and iron, we have to get the process of the supernova. And actually, there's a couple of different processes that things can go through to drive that nucleosynthesis. One's the rapid process, or R process nucleosynthesis, and then there's the slow process nucleosynthesis, and the P process nucleosynthesis, which is the P stands for proton. So the rapid process is this process by which successive neutrinos are captured before the particle can beta decay. So basically, the reason why it's called rapid is that it gains neutrons before it can fall apart. So it has to happen pretty quickly. Our process is where a lot of really interesting heavy elements come from, because you're able to basically cram things together to make a bigger thing really fast. And that happens pretty much just in supernova. So besides the heavy elements that are made in the supernova, we also get compact objects resulting from supernova, in particular core collapse supernova. So if the explosion fails, if the supernova fails, you end up with a black hole. What happens is that you get all this matter piling on to what's left from the infalling core. And if you get a high enough density of matter, especially in that small of a space, it's going to collapse into a black hole. And that's how we think we get what we call stellar mass black holes, which are black holes that are 10 to 100 solar masses. Any questions there?
No, that part makes sense. Yeah.
Okay. If the shock is successfully revived, the core becomes what we call a protoneutron star. And as matter falls back on it, because not all the matter is going to get unbound by the explosion, this ends up becoming a neutron star. One thing that's really cool about neutron stars is that they're these big balls of superfluids, which generally speaking, we've only been able to really make superfluids in the lab generally at really low temperatures, though we have recently made some pretty massive gains in what we call high temperature superfluids. And so that's something that's really wild about neutron stars, is that they are very high temperature superfluid that come about from this like extreme high density that comes from a bunch of matter raining down on this bounced core. I don't know, like, do you have questions about?
I was. The weirdest part is the repulsive strong nuclear force thing. You said that was not well understood. Like, why are you sure it's strong nuclear force doing it? Is that from models, or?
Yeah, I mean, part of it is from models, but also part of it is the fact that there's not much else it could be at those length scales. There's not much that it could be. Like, that's the regime of the strong force, the nuclear force.
And that's a lot of that is just empirical. Like, that's just.
I see.
Well, it's what we got. we know that supernova happen.
Right. That's interesting.
And we know.
Yeah, one thing you can make an argument about is that the insides of these stars, when the core collapse starts, a lot of the protons in the system are going to get changed into neutrons. And so it's like, oh, geez, how can the neutrons support themselves? Electrons can support each other. You know, they've got. You talk about Coulomb effects and stuff like that. They'll push against each other. Neutrons are electrically neutral. And so if you got a big ball of neutron matter, the only repulsive force you can think of, if they're all collapsing down on each other, are neutron degeneracy pressure. And sure enough, I mean, you blow the outer parts off of a star, and what's left behind is a neutron star. And we can see and observe neutron stars and get some sense of what they're made of and how they work, right? I mean, pulsars are just neutron stars. It's not the case that we've never seen the result of this collapse, because one possible end state is it blows off the envelope, and then we get to see whatever was in the middle of the star before it exploded.
Exactly. Basically, we know that we start off with a star. We know approximately what stellar composition is when a star is burning. And then we know that explosions happen, and we know what we're left with. From hydrodynamics, we know a little bit of what's happening, that causes the collapse, and then what happens with the explosion, at least on a macroscopic scale. And so as a result, we can kind of deduce these are the only things that are left there. These are the only things that we have at bounce, and as a result, it has to be in the nuclear force. So it's a little bit of a process of deduction.
Interesting. So it's like, is it conceivable there's just something unthought of going on there, or is this pretty well established?
It is possible. It's always possible that it's something just totally wild. But the thing is that the strong force in a lot of its relevant regimes has been pretty well tested and has obeyed the standard model pretty well. And so if it were to be something totally different, it would have to be something that would essentially reduce down to the strong force at slightly larger scales.
There was some mysterious other force we would have found it in a particle collider or something.
Yeah, it is very, very likely we would have found it in a collider, or we would have seen some evidence of it. Well, it's totally possible. It's unlikely. And when it comes to cutting edge science, that's really all we can ever say, right? Well, it's possible that it's something totally different, but let's go ahead, and if we're hearing hoofbeats, let's first assume that it's going to be horses and not zebras, and certainly not unicorns. Okay, so another thing that's really, really cool about supernovas. So, all right, we get a lot of our small black holes, we get our neutron stars, and we get our heavy element from these type 2 supernovae. Another thing that we get are cosmic rays. And these cosmic rays are really just high energy particles streaming through space. We can actually detect them here on Earth. We detect them with various experiments like Super Caramel Kande in Japan, certain neutrino detectors like Homestake, which is in a mine. Actually, a lot of these are located in mines.
Well, that was wonderful. Thank you, James. Thank you, Hanalore. You've pleased me. Your efforts have borne fruit, and that fruit is sweet. This was fascinating, so here is some fruit. James, you get the explodiest fruit. It's a popcorn.
Nice. Taste it.
And Hanalore, you get the core collapsiest fruit. You get a souffle.
That's not even fruit. It's a baked good.
Just eat it.
Nom, nom. Delicious.
All right, I'd like to thank the guest of my show, Zach Weinersmith. Thank you, Zach.
Always a pleasure.
All right, so go see Zach's webpage, the Saturday Morning Breakfast Cereal webcomic, and also you can buy his book on October 17th. It's called Soonish. It's about emergent technologies, and it's fascinating. All right, everybody, thank you very much. Well, that was really fun. Well, time for the announcements. First, again, please give us an iTunes review or tell other people about us online. Why? Because people keep their deep love of physics secret, and they want to know that there's a show like ours online, but they don't know that we exist. And also, having first-hand testimony from people they know saying that the show is enjoyable might convince them that there's some fun to be had learning physics. Thanks to the donations we've received over the last few years, I was able to hire a professional to redesign our website. It looks absolutely fantastic, and it should work as well on your phones and tablets as it does on your computers. So why don't you mosey on down over to titaniumphysics.com and have a look. I need to rewrite some of the things on the website to fit the new style, so I'd be happy to get your feedback about what you think could use a little bit of work. On another note, we're still humbly soliciting your donations. Your donations go to paying our server fees and our project to transcribe the episodes as they come out and buy everybody new microphones. I know I needed to replace my old microphone just this summer. Ugh. All right. So, if you'd like to, you can send one-time donations through our PayPal link off of our website, or you can go to our sweet new Patreon site and give a recurring, $2 donation. This particular episode of the Titanium Physicists has been sponsored by a collection of generous people. I'd like to thank the generosity of Preston Huft, Heather Richards, Albert Kalinin, Sky DeBroy, Shivang Patel, Schuler Heimlich for their donations. I'd also like to thank Sarah Stradler, Louise Pantalina, a guy named Ben, a Mr. Matthew Lambert, a fellow named Ayush Singh, a David Myrtle, and Mr. Ryan Foster, Janico Freifenberg, Steve Smethurst, Magnus Christensen, and Bart Gladys, a Mr. Stuart Pollock, our Emperor Courtney Brooke Davis, a Mr. David Lindels, Mr. Carl Lockhart, our eternal friend B.S., and Randy Dalzell, a Ms. Tina Raudio, the enigmatic Ryan, a gentleman named Crux, and Gabe, and Evan Weens, David D., and Dan Vale, a Mr. Alex, WTL, Mr. Per Proden, Andrew Waddington, Mr. Jordan Young, and John Bleasy, a Brittany Crooks, James Crawford, Mr. Mark Simon, Tucson's Gang of One, Mr. Lawrence Lee, Sixton Linnison, Mr. Simon, Keegan Eade, Adrian Schoenig, Andreas from Knoxville, Cadby, Joe Campbell, Alexandra Zani is Great, Winna Brett, Eric Dutch, Etienne, and a gentleman named Peter Fan, Gareth Easton, Joe Piston, David Johnson, and Anthony Leon, as well as Doug B., Julia, Noah Robertson, Ian and Stu, a Mr. Frank, Philip from Austria, and Noisy Mime, a Mr. Shlomo Dalal, Melissa Burke, Yassine Uurzazi, Spider Rogue, Insanity Orbits, Robin Johnson, Madame Sandra Johnson, a Mr. Jacob Wick, Mr. John Keys, a Mr. Victor C., Ryan Kloss, Peter Clipsham, Mr. Robert Halpin, Elizabetha Teresa, and Paul Carr, a Mr. Ryan Newell, Mr. Adam K., Thomas Shire, a Mr. Jacob S., a gentleman named Brett Evans, a lady named Jill, a gentleman named Greg, thanks Steve, Mr. James Clausen, Mr. Devin North, a gentleman named Scott, Ed Lowlington, Kelly Weinersmith, Jocelyn Reed, a Mr. S. Hatcher, Mr. Rob Abrazado, and Mr. Robert Stietka. So that's it for the Titanium Physicists podcast this time. Remember that if you like listening to scientists talk about science in their own words, there are lots of other shows on the Braculo Media Network. Look us up on iTunes. The intro song to our show is by Ted Leo and the Pharmacists, and the end song is by John Vanderslice. Good day, my friends, and until next time, remember to keep science in your hearts.
I gotta tell you, dear, before you come back here. I lost your bunny. I let him out of the cage. He was eating spring mix on the carpet, jumped into the haze. Hop down Magnolia Boulevard, no way he'll survive.
But the thing is that it's really, really hard in the simulations to get neutrinos alone to get this explosion to revive. Because again, neutrinos do not have a lot of mass, and you're having to get a lot of energy. So something else that's interesting is that, and that we're starting to have the computing power to test in simulations, is non-symmetrical effects. So it's easiest to simulate something that's spherically symmetric, because then it's basically just one dimension, right? You just have to worry about the radial position. But now we're simulating fully 3D. And so you can get these asymmetric effects. So one example is called the standing accretion shock instability, also known as SASI. It's thought that these kind of create a bit of a sloshing mechanism that can help with the revival of that shock. Sort of like if you were to then take that pot of boiling water and then grab the handles and kind of shake it back and forth, that would start helping to shake off the lid a little bit faster, right? And one reason why we think this sort of thing has to happen is because when we see these observations of neutron stars and a lot of these smaller stellar mass black holes, is they actually have what we call a momentum kick, which is to say that there's been momentum imparted on these objects. And if it were spherically symmetric, that wouldn't happen. It would all balance out. But these are given an initial kick of momentum. And from what we can tell, things like SASI are the most likely to impart that.